Hey everyone, we're going to talk about the Heisenberg Uncertainty Principle today. My name is Jenson Rawlings. I'm doing this for the final video presentation in Physics 106 this semester. So we talk about Heisenberg first, right? A lot of us, when we think of the name Heisenberg, we probably think of this guy from Breaking Bad who called himself Heisenberg. And he called himself Heisenberg because he thought Heisenberg was a fantastic scientist-chemist. This is the real Heisenberg, Werner Heisenberg. He was a German physicist who came up with this uncertainty principle back in 1927. I believe he won the Nobel Prize for it as well. So when we talk about the uncertainty principle, one of the best ways to apply it is with electrons. We know that electrons exhibit wave-particle duality and that they can exist depending on how they're observed as either waves or as particles. So their movements around the outside of an atom, originally by Bohr, were thought to be kind of like these orbitals, where they just get to be drawn and kind of can jump from energy level to one energy level to the next and back down. And they had these discrete momentums and velocities, and we could predict their position essentially at any given point in time. We know now through experiments, and partly because of this Heisenberg uncertainty principle, that that's not exactly the case, and that the electron orbitals can be modeled better with probability clouds based on where they might be and where they cannot be. We can see here we have these hydrogen waves and all the different orbitals that could exist out of a hydrogen atom, right? So like we have the s orbitals here, some of the p orbitals, based on the energy, based on the spin, based on interactions with other electrons in the atom. And so we have these probability clouds that were defined by the Schrödinger wave equations. So when we think about uncertainty, there's kind of an intuitive way to think about it. So if you see somebody running down the street, you can either sit and watch them go by and know exactly how fast they're going, but have no idea where they're headed, or you can stop them and talk to them on the street to find out where they're headed. If you are sitting and watching them and not knowing where they're headed, then you've got uncertainty in their direction, their end goal, essentially. But you have certainty in their velocity. And if you stop and talk to them, then you may have certainty in where they're headed, but you've lost all certainty in how fast they're going. And so it's not exactly the same with electrons and with other particles that have this wave-particle duality, but the intuition is kind of the same. We can either know where something is or how fast it's going, but not both at the same time. And so if we look at some of the math behind this, we can look at the momentum. And if we know for sure exactly where an electron is, if we use a very short wavelength interference and we knock one of the electrons out, we can know exactly where it is. And we can use this equation where delta x times delta p is approximately equal to h. And that's if we knew exactly, precisely x or precisely p, where p is the momentum. But we would have to then give a larger uncertainty to the other. This equation is derived by saying that your uncertainty in position is approximately equal to the wavelength of the photon that will knock the electron out of place, and that the uncertainty in momentum is approximately equal to Planck's constant over the wavelength. And so when these are set equal to each other, where we can substitute in delta x for lambda, we can get delta p equals h over delta x, approximately equals, I should be doing. And then we turn that into delta p times delta x approximately equals h. And so the idea that Heisenberg came up with is that the maximum certainty we can have if we try to measure both position and momentum simultaneously is given by this equation. Delta x times delta p approximately equals h over 4 pi, which is also equal to, not approximately, equal to h bar. It's a separate variable, but it's given here with h over 4 pi. And so we can measure anything at the same time as position and momentum, only as precise as h over 4 pi. This uncertainty principle applies to other things. It applies to all particles in terms of velocity, momentum, but also applies to energy for a couple of reasons. One is that energy is really hard to measure in a very specific instance in time. Things can jump around, right? Electrons can jump from one energy level to the next and back down at any moment, any given time. Or things, subatomic particles may only exist for millionths of a second at a time. And so to measure the energy during that time is very difficult. And so the same principle here. So the change in energy delta E times the change or uncertainty in time is equal to h over 4 pi. Basically, the shorter the amount of time that you measure the energy in, the greater the uncertainty in the actual energy overall is. For example, if a particle only exists for a fraction of a second, and we measure the energy for that fraction of a second, we don't know all of the different paths that the energy took during that fraction of a second as it degraded, as it was created. And so all of these are elements of this Heisenberg uncertainty principle. It really works at a subatomic level mostly because larger macroscopic things are easier to measure and to quantify. And so some of the applications of this is where we get electron orbitals from, because we, like I said before, we only have these probability clouds. We can't map exactly the path of an electron around it. By measuring its position, we've thrown off its momentum. By measuring its momentum, we've thrown off its position, etc. This all leads to quantization, right? If we look at these electron interference patterns from the double slit experiment, we can see that these are existing in specific wavelengths, partly because of this uncertainty principle, where we can either know, if there's large enough amounts of these electrons, we can measure them as waves, and if there's just one, we measure it as a particle. And so we measure those waves as the quantization. This also leads to the violation of the conservation of energy in very small instances. This helps to explain things like Einstein's postulate, special relativity. It also helps form the basis of the strong nuclear force and other things like that, where matter can be created and destroyed without anything else there because of the energy. And there's no way for anyone who measures it or any physicist to say that the law was broken, nor is there any way for nature to say that it was broken because of this uncertainty principle. So it allows for this kind of ambiguity at the subatomic level. One of the quotes that kind of illustrates this, what was quoted in the textbook, is what there are particles. And this goes back to this kind of ties all three of these together, that because, when there's enough particles, that there's enough probability, we see them as waves. That's what essentially allows things to be solids, that allows things to be have material shape, all these particles interacting and forming these waves of probability, whereby we interact with those waves. So that's the Heisenberg uncertainty principle, some of the applications of it. Here are my references. I hope you guys enjoyed it.